20 minutes and you get this. But of course, you have to adjust it. When you report the volume, you have to adjust it back to STPD, right? So it is standardized volume. Okay, so this is the difference of the oxygen, the fraction of the difference of the oxygen being utilized. Multiply the total volume of the expired air, the output air. Okay, so then you get total liters of oxygen being used per minute, and multiply by 5. This equation says it's 4.92. Okay, close to 5. Usually we can use 5 also. That means 5 kilocalories equivalent to 1 liter of oxygen consumed. If we use this approximation of 1 liter of oxygen or 5 kilocalories of energy, then this equation is like this. It's the same, right? Except this constant, 4.92 or 4.5. Because 1 liter of oxygen consumed or burned will produce 5 kilocalories of energy. So this equation the idea is very simple. The only thing is, how do you measure this and this? Okay? Okay, with just 1 or 2 wires and with a mask, it does exactly the same thing as the Douglas bag. Okay, and then it produces real-time measurement of your oxygen consumption. Okay, and this is some of the fancy machine. But today we have something even better, right? Today we have some smarter device, okay, which measure based on your finger, which measure the oxygen concentration, the oxygen concentration in your blood. Okay. So with this kind of technique, okay, we can also correlate this information with the energy consumption. So you can actually, okay, with a finger right here, put it here, and then it will show you the oxygen concentration. Okay. Okay, so now we are able to measure the total volume of expired air. Okay, that's called V dot E. Dot means per minute. That means the speed. Liters per minute. And then we are able to measure fraction of air expired. Okay, oxygen. Fraction of oxygen in the expired air, okay, and then we can estimate the energy consumed per minute, okay. But remember, we have to report the volume in STPT. So how do we do that? Usually we do this correction. STBD correction, okay, you use this formula. Okay, 273 divided by 273 plus the temperature at the measurement time, moment. Okay, and then PB is the barometric pressure at the measurement time. At the measurement time. Okay, so for example, what is the PB today? You can check the weather bureau in Taipei today. I don't know. Maybe on your phone it shows you already. Sometimes it's 760. Sometimes it's a different one. Every day this is different. And how about the water pressure? Water pressure is the vapor tension of water at the temperature of the gasometer. Gasometer is the device which measures the volume, the air, which is obtained from the empirical tables. Okay. So here, this is a table. At different temperature, okay, for example, 12 degree, the vapor pressure is 10.5. Okay, 25 degree, the vapor pressure is 23.5. Okay, and then with this correction, let me show you an example. Okay, this is the one example, pre-test measurement. The subject body weight 75 kg, subject height 178 centimeter, weight of subject clothes 4 kg, weight of pulmonary gas meter 4 kg. Okay, looks like he's wearing something, a mask, pulmonary gas meter, and experimental measure. Okay, gasometer, that's the measurement device. Reading started at this time, hours, minute, second, 10 in the morning, and then gasometer ended at about 10 minutes later, right? 10 minutes, 30 seconds later. Then we stop the experiment, stop the data collection. So now we have the total duration. Initial gasometer reading before we start, okay, it shows this, the gas it contains, the reading shows this. And final gasometer reading, the gas it contains shows this. So the gas, the volume increased. Okay, about 200 something liters. Within 10 minutes, then you collected so much air, so much volume, so much gas. And the temperature at that moment is 25 degrees. Barometric pressure is 755. So obviously this place is not at the sea level, I think. Okay. It's a lower barometric pressure. And the oxygen content of the expired air we collected and measured is 16.5%. And the oxygen content of the expired ambient air is same. Okay, 20.93%. And then let's use 1 liter equivalent to 5 kilocalorie. With these information, then we can calculate. Let's first get the total volume expired, total output volume from your body, VE, which is this value, initial reading minus final bidding, which is a 336 liter. So 541.5 minus 205.5. Yeah, it's 541.5 minus 205.5, right? So this minus this. So it's about 336 liter. And this subject, this person, looks like he's doing some work. Okay, so the total time duration is 10.5 minutes. And then he produced so much volume, output air. And then we correct this, okay, by doing this conversion. So you plug in this, okay, the current, barometric pressure in the air, and the water pressure. Okay, you look up that table. It is a 25 degree, okay, so the 25 degree so the vapor pressure, water vapor pressure is 23.8. So 23.8, we use it here, okay, and then we correct it. So the correction factor is 0.881, and then you correct the 336 liter by this correction factor. So what does that mean? That means if you were doing this experiment in Taipei at the sea level, and if that particular day the air pressure, barometric the pressure is 760 mmHg, the volume will be only this, not this big. However, if you are doing it in Bandung, maybe it's this. So you have to correct it back to sea level. So actually the air output is only 296.1 liter per 10.5 minutes. Now we are ready to plug in that equation. So V dot E would be 296.1 divided by minute total duration. So now we know the air output from the body is 28.2 liters per minute. And then V dot O2, the oxygen volume per minute would be this, 28.2 multiplied by the fraction difference. 20.93 is a fraction of the fresh air of the oxygen. 16.5 is the fraction of air in this one, in the expired air, 16.5. So that means some oxygen has been utilized, right? The fresh air contains 20.93, but after you do some work, the output air contains only 16.5. Okay? So this fraction difference is the one being used. So totally divided by 100, that will be 1.25 liter, 1.25 liter per minute. So that, what does that mean? That means during this period, 10 minutes, during this 10 minutes, this guy is using oxygen, is burning oxygen at this speed. Every minute he burns 1.25 liter. And then you multiply this by 5 kilocalorie per liter. And then adjust it back to, you don't need to adjust it back to hour, but this example, they adjust it back to per hour for some reason. Usually we just report per minute. So 1.25 multiplied by 5 will be, what is the read? 1.25 multiplied by 5?
6.25.
6.25? Is that right?
Yes.
6.25? Okay. So this job consumes 6.25 kilocalories per minute. And the standard today, the international standard, is to maintain the job below this value, 5 kilocalories per minute. That's considered to be a fair job, both for the worker and for the boss. 5. So this is a little over 5. How do you do? So it's not fair, right? If you ask this person to work for 8 hours, that's significant amount of over workload. Significant amount of over workload. So how do you solve this problem? We're engineers. We can provide engineering solution to reduce the job workload to this level, right? That's engineering solution. Automation, human-robot collaboration. This is a very hot topic now. Part of the job, you ask the robot to do it, and then so the human can lower the workload. How about management solution? Managerial solution, management solution. That's easy. Ask another person to help and share the load. So 2 people working. Now it's reduced. Or rotation of the workers. We've been talking about this rotation. Job enrichment. Rotation. Yeah. You only ask this guy to work at this workload for the morning. And then in the afternoon, you ask this guy to do other thing. And then over the 8 hours, the average is within the standard. That's management solution. Correct? But if you don't want to increase the cost, see, engineering solution requires money. You have to buy the robot. You have to buy another machine. Management solution requires money too. You ask another person to help. That's cost. Okay? Ergonomic solution. How we reduce it? By giving this person appropriate, optimal amount of rest period, so that over the 8 hours, totally on average, it's reduced. So that's work rest schedule. We'll talk about it later. Okay, I just describe this one. It's called work rest schedule. So what is a fair day workload? A man of average physique working without carrying a load in a straight line on level ground at speed of this ILO. They proposed this in 1979. I think we discussed this last time. The average man is this. The equivalent energy expenditure is this, about 5 calories per minute. So that's the standard today, about 5. So what is the fair day workload? About below 5 kilograms per minute. See, if you calculate this is per minute, right? What will be the total for 8 hours? 6.25 times
times
60 minutes
times 8.
times 8 hours. What will be the total? Huh? 3,000. Whoa. Okay. What about this? 5 times 60 is 300. It's about 2,400. But actually this guy recommend 2,000 only. So anyways, if this is the standard, if this 5 per minute is the standard, 5 per minute is the standard. So that means per day, you only allow for 2,400. So now we have a problem. It's through 3,000. We have 600 more. So how do you give the rest duration so that, okay, maybe you can allow him to rest for 1 hour and only working for 7 hours. Let's try it. If 7 hours, what's going to become 7 hours? What will be the result? 2,600. Okay, 2,600, close. So that means if you ask this guy to come to the job, he can only work for about 7 hours, a little less than 7 hours, to keep up with this. That means within the 8-hour work period, he needs 1 hour rest. He needs 1 hour rest. Okay? So what you can do is this. This is 8 in the morning. This is and usually from 8 to, or from 9, sorry. How about this? 9. That's 8 hours, right? Only 8 hours. Okay. So you can do this. You ask this guy to work and then off here. And then go home. Right? So this guy only work for 7 hours and then go home. That's one possibility. Is this good? Yeah. Some company they prefer this because most operator, most worker, we prefer this, right? Because you can go home early. What is the disadvantage of this? Okay, imagine if he is not working at this. He is working at this. Very heavy job. What's going to happen? If you use this approach, he will be off here. And then go home. Right? Very heavy job. He only works for 3 hours per day. And then you go home. What is the disadvantage of this? What's going to happen to this guy? He's over workload. He's overloaded during this period. The next day he's overloaded again. The next day he's overloaded again. After about 1 or 2 weeks, his quality, his productivity will decrease. Eventually, it's not good to the boss. Workers may prefer this because they have more free time. So what is a fair management strategy? Another idea is to allow certain rest somewhere. Evenly. And work, rest, work, rest, work, rest, work, rest, until 5 p.m. So you distribute the rest evenly. I think this is a better option, right? Because the rest is designed for not only the 8-hour period to be fair, but also the rest. You take the rest for the next work duration. So you will not be overloaded. Right? So this is an ergonomic approach. And how to calculate this? This is the idea is quite easy, okay? Okay. This one is listed in the major ergonomics textbook. Okay. This equation actually originates from this, okay? TR is the total recovery time in minutes, total duration, total resting time. TS is the total work shift length. Okay, for example, if your shift is 8 hours, that will be 480 minutes. So this will be 480. M is the average energy expenditure here. So let's try it. Now M is 6.25. So now we have TS is 480 minutes. And then M calculated to be 6.25 per minute. Now we have an example which is 6.25 kilocalorie per minute, this job. And suppose that guy is working continuously. S is the level of energy expenditure adopted as a standard metabolic rate for the entire work shift. So S is the standard. The standard, okay, we can use for male usually is 5. For female, we can use 4. Okay, suppose this is a guy, so now we use 5. That is why major ergonomics textbook simply put a 5 here, 5. Okay. And then 1.5 is the resting level or basal metabolic rate for an average man. So it's 1.5 here. Okay? So in this example, it's very simple. So M 6.25 minus S is the standard is a 5 divided by 6.25 minus 1.5 multiplied by 480 minutes. Okay, so what is the result? Total rest is what is the result?
$126.
126?